All right, hello everyone, welcome. My name is Adam, and I'm here to tell you all about locking chefs in kitchens, and also about SBOMs, maybe. To briefly introduce myself, I work at Red Hat on a project called Conflux, which is a CI/CD system focused on supply chain security. It happens to be Red Hat's main build and release pipeline for container images. But all you really need to know about me is that I maintain our build pipelines, and I care about the accuracy of the SBOMs that we produce. In this talk, I'll be going over what is an SBOM, just very briefly, the typical approaches to generating SBOMs, mainly the ones that we've tried and where they fall short, and finally, the approach that we currently use, based around a tool called Hermetic. So, what is an SBOM? The acronym stands for Software Bill of Materials, but to be honest, that doesn't mean much to me. I like to think of it as an SBOM being simply a list of ingredients. When I buy a pack of instant ramen, I expect to find the list of ingredients on the back. I may want to check if I'm allergic to any of the ingredients. Similarly, when we download a piece of software, we are slowly beginning to expect to find the list of ingredients for this piece of software. For example, if we were to download the universal base image 10 from Red Hat's container registry, we would find its SBOM, which would be a JSON file, could also be XML, in a format defined by one of the SBOM standards, typically SPDX or CycloneDX. In this file, we would find all the ingredients or all the packages installed in this container image. And we may want to check if any of them are affected by vulnerabilities, for example. But how does one go about generating such an SBOM? Well, one option would be the analyzed SBOM approach. This is where we go to a restaurant, the waiter serves us a bowl of ramen, and we try to figure out what ingredients went into it just by inspecting this bowl of ramen in front of us. Or, if we are maintaining a build pipeline, if we are running the restaurant, this is where we first let our chef prepare the ramen before taking it and working backwards to try and figure out what ingredients the chef used, which seems like a silly approach, but it may well be the most popular approach to generating SBOMs. In the world of container images, this approach is where we take a container image and run it through a tool like Sift or Trivi. This tool analyzes the image and outputs an SBOM. And this works surprisingly well, because most types of software packages come with metadata that helps identify them even after installation. So if we were to take the UBI10 micro image from earlier and run it through one of these tools, we would get an SBOM listing fairly accurately all the installed RPM packages. So the approach isn't as silly as it may seem. But of course, there are corner cases. And of course, one of them is JavaScript. If we were building a simple JavaScript frontend, our Docker file or container file may look something like this. In the build stage, we run yarn install to install our JavaScript dependencies, and then we execute webpack, which is something called a bundler and minifier, but more about that later. In the build stage, all we do is copy the content that we already built in the build stage. Now, if we build this container image and analyze it, we get back one single dependency, just busybox. And this one comes from the parent image that we used for our final stage. But where are all the JavaScript dependencies that we downloaded? If we take a look at the content of the image that we just built, there's only two files of interest inside, index.html and bundle.js. What happened is that Webpack took our source code, the source code of all of our dependencies, and bundled it into this one huge blob of JavaScript. This is as if, before attempting to analyze that bowl of ramen, we first took the ramen and put it in a blender, and then tried to analyze the results, which would be impossible and disgusting. So the problem with the analyzed SBOM approach is that it is not always possible to identify the installed packages. They may have gone through Webpack or any other kind of blender. And even if we can figure out what is inside, we usually cannot tell where it came from. And if you've heard of the dependency confusion attack, then you may know that the same package coming from two different package registries may not be the same package at all. But here's a different idea. We are running the restaurant, so we also have access to the recipe. And the recipe already includes a list of ingredients. Why don't we just use that? Well, here's a problem. Our recipe for ramen just says that we need ramen noodles. But we are a fancy ramen shop and we make our own noodles. The chef knows how to do that, so that's not a problem. But how will we know, just by looking at the recipe, what ingredients the chef will use? We will not. But luckily, most programming languages have package managers. And these package managers typically use log files. For example, JavaScript has yarn, among many other package managers. And yarn uses a file called yarn.log. In this file, the package manager lists not just the direct dependencies, not just our ramen noodles, but also the dependencies of those dependencies, and so on. The full transitive list of ingredients. So if we were to run Sift on the sources of a JavaScript project, we would easily get the full list of ingredients. Or would we? Can we really be sure that the log file is complete and up to date and that it fully covers everything that will happen during the build process? Or that it's even there in the first place? And for another example, let's look at Python, where in my experience, most projects use the good old requirements.txt files to specify their dependencies, even if there are now better options available. Given just a requirements.txt file, do we have the full list of ingredients? Well, that depends. The file could list just the direct dependencies. It could just say ramen noodles. It could be the full transitive list of dependencies, or anything in between. So if we run Sift on the sources of a Python project and we get some dependencies, do we have the full list? We don't know. So the problem with the source SBOM approach, well, it does work for JavaScript with some conditions. It does work for Python with some trickier conditions. And the same could be said for most packaging systems, except for those that do not even have the concept of a manifest file where the user would declare the dependencies. And this would be most of the operating system level package managers, such as RPM, used by Red Hat Linux and others. But for those, the analyzed SBOM approach tends to work pretty well. So why not both? We have the recipe, we have the final product, we can analyze both, combine the results, and maybe that will cover the gaps. Maybe when we scan the sources of a Python project, we get nothing, but then we scan the final image and we get the full list of dependencies. Or maybe we scan the image for a JavaScript application and get nothing because the dependencies went through a blender, but then we scan the sources and we get the full list of dependencies. So yes, combining the approaches does help. It does increase the chance of getting a complete SBOM, but should it give us full confidence that the SBOM is complete? No, not even close. But let's address an obvious question. We are running the restaurant. Why are we only looking at the recipe and the final product and ignoring everything that happens in between? We are a build pipeline. Shouldn't we be generating the SBOM during the build? Yes, we probably should. But how? We would need a tool that can take a container file, Docker file, and build a container image while generating an SBOM based on every possible action that this container file can do. And that is infinitely many possible actions. Does such a tool exist? Kind of. Podman Build, for example, does have an SBOM option. And the same goes for many tools that build containers. But all they do typically is our combined approach. They scan the input, scan the output, and combine the results. So yeah, generating an SBOM at build time would be great. But I don't know of any viable way to achieve that. But this brings us to the Hermeto approach to SBOMs. Going back to source SBOMs for a moment, is the approach conceptually broken? The problem was that we could not be sure that the recipes listed all the ingredients. The problem was that the chef could go and get extra ingredients that were never mentioned in the recipe. So why don't we stop the chef from doing that? Why don't we go through the recipes ourselves, provide the listed ingredients and nothing else, and then lock the kitchen? How about, as the build pipeline, we clone the user's source repo, identify all the dependencies, download them ourselves, provide them to the build step, and then cut off internet access. Now, the build isn't able to get any dependencies other than the ones that we explicitly provided, and the SBOM that we get from the prefetch step should be complete. And that's where Hermeto comes in. Hermeto is a CLI tool that prefetches dependencies. Like many source SBOM tools, it reads manifest files and outputs an SBOM. But unlike those tools, it also downloads the identified dependencies and arranges them for offline installation. Currently, Hermeto can do that for the package managers you see on screen. That's Bundler for Ruby, Cargo for Rust, Go modules, NPM and Yarn for JavaScript, and pip for Python, as well as a generic fetcher for those cases where we need to install something directly from a URL and we have no better option, and to some extent, RPM packages, but at the moment, those have many caveats, and that's a story for another time. How does it work? Sticking to the example of JavaScript plus Yarn, Hermeto gets a source repo as input, reads the manifest files and the configuration files, identifies all the dependencies, and downloads them from the package registry. As output, we get a directory with an SBOM file and all the downloaded dependencies. We also get a list of environment variables that we need to set to make the package manager work offline. For Yarn, that would be an offline mirror variable, pointing to the dependencies that Hermeto downloaded, as well as a variable that turns off offline mirror pruning, but we don't need to worry about that one for now. If Yarn didn't support environment variables, or if they were not enough to enable offline installation, then Hermeto would instead, or additionally, output configuration files intended to replace the original ones in the source repo. For Yarn, that could be a Yarn RC, setting those same options just as a config file. In terms of using the actual CLI, it looks like this. We start with the fetch deps command, which downloads the dependencies and gives us an output directory with the SBOM and the downloaded dependencies, arranged as a Yarn offline mirror, which is quite simply a list of tarballs with specific file names. Next, the generate env command gives us the list of environment variables that we need to set to make Yarn work offline. And finally, the inject files command does nothing because it doesn't need to do anything specifically for Yarn. If we were dealing with a different package manager, or if Yarn did not support environment variables, what it would do is overwrite the configuration file directly in the source repo to set the options required to enable offline installation. OK, we have the output directory, and we have a list of environment variables. What we want to do is build a container image. How do we do that? Let's say we are using podman build to build our containers, which works the same way as Docker build, more or less. The first thing we need to do is make the output directory available. To do that, we can simply use the volume option to mount the directory into the build. Next, we would have to set the environment variables that Hermeto is telling us to set. There's more ways how to do that, but the simplest one to show is to use build arguments. We would first need to declare those in the container file, or Docker file, and then supply their values on the command line. Finally, but most importantly, we would add the network none option. And this is the reason why we even bothered with Hermeto in the first place. This is the part that cuts off internet access and ensures that the build cannot get any dependencies other than the ones that Hermeto explicitly provided. And believe it or not, this usually works. But what did we achieve? If we go back to the Webpack example, which defeated the analyzed SBOM approach, Hermeto reports the dependencies just fine, but so do most source SBOM tools. So what's the difference? The difference is confidence. The difference is that if we run a source scan and then a regular build, we can say that maybe we have a complete SBOM if all the stars aligned. But if we run Hermeto and then a network isolated build, we can say we do have a complete SBOM with no ifs and no maybes. What if we don't have a complete SBOM because some dependencies were never declared in the source repo? Well, that's easy. The pipeline fails. Either already while prefetching, if Hermeto is able to detect that some dependencies are missing, or later during the build phase, if Hermeto is not able to detect that, in which case Hermeto simply downloads all the dependencies it knows about and leaves it to the build step to fail if some dependencies are missing. So, to summarize, Hermeto is kind of just a source SBOM tool, except it also downloads the dependencies. Hermeto doesn't really do anything special to make the SBOM complete. Hermeto relies on the user already having a complete manifest of dependencies in the source repo. And Hermeto isn't always able to detect when some dependencies are missing, but relies on the build process to fail when that's the case. But Hermeto makes that easy. Hermeto makes it easy to do network-isolated builds, which give us the confidence to say that the build works if, and only if, we have a complete SBOM. So you might say, Hermeto by itself doesn't do much of anything, does it? But when integrated in a larger CI pipeline that properly makes use of Hermeto, it can be fairly powerful. One such pipeline is, of course, Conflux, Red Hat's primary build and release pipeline for container images, where enabling a Hermetic build can be as simple as setting 2 parameters in a YAML file. But if you'd like to know more about Conflux, then come see a talk tomorrow called Who Are You Building For? Pipelines Have a Purpose by my colleagues Andrew and Julian. And that's about it for me. Do you have any questions? Go ahead.
If you're pushing back upstream a larger list of the dependencies, yeah, which presumably you're doing, do you get any pushback from any maintainers who feel that you're messing with the amount of detail they're happy with?
Can you repeat back the question?
Right. The question is, if we are requiring the user to push the full list of dependencies upstream, do we get any pushback from the maintainers? To some extent we do, but currently all of our users are Red Hatters, so they don't really have an option. Go ahead.
Here, hold on one second.
I just wanted to know that what's the difference between Hermeto and tools that are used in the air-gapped environments like Hopper, for example?
Sorry, what was the name of the tool?
Hopper.
Hopper. Okay, the question is, what is the difference between Hermeto and tools that are used in air-gapped environments like Hopper? I have not heard about Hopper, so if you can give me more info after the talk, that would be great. Honestly, I don't know if there's any difference. Go ahead.
So in some environments, when you go to build things, it'll actually look for like binaries and things on the local system that fulfill some needs. And so those, with the way you're doing things, I think wouldn't be captured in your SBOM. So that is a asterisk like?
Yes.
Okay. Okay.
So I don't need to repeat the question, right?
No,
Okay.
Can you comment on that?
Yeah. So that's a very big asterisk, which I sort of conveniently swept under the rug for this talk because it's only 20 minutes. But yes, that's a good point. I would say Hermeto's purpose is it cares about the sort of net new content that enters the build and doesn't care as much about content that was already present. So in the context of building a container image, you already have a lot of content coming from the parent image. That was, after all, I mentioned that on the slide with BusyBox, right, around here. So Hermeto would not be aware of that. The purpose of Hermeto is to capture all the new content and not as much the content that was already present. That would have to be handled in sort of the larger context by the CI pipeline that integrates Hermeto. And we do handle that in Conflux to some extent.
Or you could generate attestations and look at what's happening during the build process would be the other way to detect those types of things.
Or you could reduce access to certain directories where those things are likely to be.
Or you could reduce access to certain directories where those things are likely to be for the recording. So
I'm not sure how it would work with the attestations. I'm not familiar with that approach.
let's talk offline. We can talk afterwards.
Good.